All right, good evening. So today's plan, I really want to finish the math review. That should be quick. You guys studied that a year ago. So once I mention the concept, it should just come back immediately, I hope. But we're going to do some exercises and then walk you through. And I definitely want to start you fresh next Tuesday about temporal logic, LTL. That's something we'll do next Tuesday for sure. Okay, but today, let's get it through. And of course, for those of you who didn't take 3342 with me, interrupt if you got any question. That something you definitely have not seen before and you cannot understand. All right. And quick reminder just before we get to the logic. Okay. Over here. So guys, apology again. I lost your lecture recording from Tuesday. Sorry, but if any part you find you want me to repeat, drop by my office hour. We'll talk about it. All right? I'll try not to let it happen again. Lab number 1, make sure you complete it. And part number 2 will be released, for the tutorial video, will be released by the end of the coming Monday. That'll be a second part to show you how you can do model checking and also some debugging techniques, especially to study the state diagram and also to study the error trace. That's something you will have to know for later labs and also for sure for your programming test. All right, that's about it. Guys, do you have any question about Lab 1 you want me to address right away? Anything? One thing you may want to know, I just sent you an announcement before the class. Maybe I don't need to show. So you just go to eClass and re-download this the instruction PDF. And there were a few hints I added for developing the second refinements. And thanks to Patrick. So that's something he thought we should really be useful. Okay, very good. So let's now get to propositional logic. The main thing I want to talk about will be implication. Okay, implication will definitely be important not just for the not just for temporal logic, but when we get to the second phase of the course later, which is about program verification, we also need. All right. Yeah. So guys, please. Okay. Implication. And you know P implies Q. And luckily, in TLA plus, you just say equal and larger than, right? That's the implication you have to write. And P implies Q. And how do we understand P implies Q? I just want to walk you through very quickly about how you can understand the truth table. Okay? You just need to know some analogy. Let me get to it right away. One possible analogy is to think about, let's clarify the term first. If you look at P implies Q, P over here is called antecedents, assumption, or premise. For Q here is called consequence or conclusion, right? So that's a standard term. You can use either one. And then let's now talk about some analogy quickly. That's how you can derive the truth table for the implication in case you forgot, right? Let's walk you through the basics, okay? When we talk about implication, if I got, let's say, P implies Q over here, right? You can think of P over here is something that's promised. Promise term. For example, let's say salary should be paid. Right? Certain salary is actually promised when you sign a contract. And over here, let's say another one, the Q over here is the obligation, given that you get paid. Obligations. Of course, for example, you have to do some work. Okay? And now how do we use this kind of analogy to draw the truth table? How do we do that? The simplest case will be, so now you want to think about P implies Q. We say that this will be true if the contract is not breached. So that's how I use this example here to remind myself about the truth table. Just remember this principle. If the contract itself is not breached, then implication should evaluate to true. Let's talk about different cases. Because we got P and Q over here, each one of them can be either true or false. We got 4 cases to talk about, right? The simplest case is the most ideal. Case number 1. Okay? Let's say if P is actually true, and also Q is actually true. What does it really mean? That means the salary is paid and the employee does the work. That's win-win, right? In that case, is the contract breached? Not really. So in that case, it's really satisfied, it's honored. So the implication would just be true. So this will be one row you will see on the truth table for implication. Right? That's one. Let's do another case. Let's say P here is true. You do get paid a salary, but somehow you escape from the work. Let's say you didn't do it. You didn't fulfill the obligation. That means the Q would just be false. In that case, was the contract breached? Absolutely. In that case, it would be false. Right? So these are the two cases that are more meaningful. The next two cases will be trivially true. Because, let's see, for case number 3 and case number 4, it's going to be, I'm going to use a different color here. When P is simply equal to false, what does that mean? You signed a contract for work, but somehow the employer never pay you. And then, does it really matter if you work or not for the contract to be breached? Doesn't really matter, right? Because it's simply not satisfied, right? So in this case, you'll say Q over here either true or Q here either false. Doesn't really matter, all right? It would just be true. The only case you can breach the contract is when you get paid, but you didn't do the work. That's the only one. The other ones, they are simply just true. And I want to also remind you, later on, when we analyze the model checking the temporal properties, sometimes we have to do some paper justification. So usually when it involves the implication, very often we may have to consider these cases because when the premise are simply false, in that case, you can easily get true result trivially. Okay, just keep that in mind. We'll see example later. So here, this will be very common base case or trivial case for justification. And we'll see example very soon when we talk about quantification, when we review it. All right, any question? All right, make sure you understand the truth table. That's the first one, all right, implication. Let's go back here, and everything has been set. And the next one. So this one here is talking about when you got P implies Q, but there are different ways you can express it. For those of you who actually saw this before, do you guys remember how many? About 4 or 5, right? Something like that.
And so are you using De Morgan's too?
No, actually, there's no De Morgan over here. Huh? Oh, yeah. Okay, anyway. So let me give you an overview very quickly, right? And then we'll go through each one of them very quickly. It's right to the point, right? When people say in English, Q if P, they really meant P implies Q. That's number one, okay? Don't worry too much about the explanation here just yet. I'm going to explain that in a moment. The second way would be P only if Q. And notice one thing here. I put Q here, I put Q here. The order matters, all right? It's not arbitrary over here. That's the second way. Or you can say P is sufficient for Q, the third way. And the next one, Q is necessary for P, all right? The final one, Q unless not P, all right? Huh? Which are there's really not best one. I think if and only if are really often talked about, if you want to prove equivalence, right? When you prove if and only if Q. I think sufficient is also talked about very often too. I don't really hear unless very often. However, there will be an operator in LTL, which we'll start talking about next week. It's called unless operator. So this might be useful for later. Yes? Yeah, if you say if P, then Q, yes, that can work too. Maybe that's too trivial, so that's why I didn't list it here. Right? Yeah, that's quite obvious, right?
That's like the most common.
Yeah, you can say that's common. I wouldn't disagree, yes. But these are also quite common too, right? Absolutely. Did you have a question here before? The same thing, good. I definitely wouldn't mind to put if P, then Q, for sure. All right, so let's now go over each one of them very quickly. So the way I want to present it will be just to show to you how to understand each one of them by referring to the truth table. Of course, they're referring to the same truth table for implication, the same. Let's take a look at them very quickly, and then we can finish the slides. The first one, Q if P. In some way, that's pretty much like what you guys were talking about. If P, then Q. Very similar. This is to say, Q would be true if P is true. So knowing that P is already true, Q must be true. Okay? So let's now take a look at the truth table. For this one here, let me help you understand when you study this note later. I kind of group these two together. So Q if P, and also P is sufficient for Q. These two can be understood as the same way. The way to justify their meaning is very similar, or to present their meaning. Similarly, P only if Q, and also Q is necessary for P. They can also be understood in a very similar way. And Q unless not P, just stand alone. Okay, we'll just go over one by one. Let's go over Q if P first. The way I would suggest you understand is like this. Think about over here. This is specifying some causal relationship. To say, if, like what you boys said, if P is the case, and then Q, right? Only if this is the case and this is the case will we actually get true for the implication. The causal relationship will actually be satisfied. So I'm going to highlight just this line over here. This one to say, if P is already true, and also Q is also true, we know that this causal relationship would just be true. It's satisfied. That's the only way to make it satisfied. Symmetrically, if I know over here, P, I know it is true. However, it does not cause the Q to be true at the same time. So that means the causal relationship is violated. So that's why it's false. All right? And what if the cause over here is simply false? That means there's no obligation for this one to be either true or false, and so there's no way to violate the causal relationship in that way. So that's why these are both true. I'll write it down here. It's like a don't care case. So these two over here, when the cause is not true, then it doesn't matter what the consequence would be. Consequence is the causal relationship would just not be violated anyway. Causal relationship is just not violated. Are we okay with this one here? So? Let me try to see if I can help. Is there any part that you find a little bit weird that I can help a bit? We just need a bit more time to think about. Oh, I'm actually your classmate behind. Maybe, you need more time to think about it? Okay, no problem. That's fine. If there's anything that's really bothering you, let me know, right? Otherwise, I'll assume you guys are okay. And you will see later in the slides, when I say P is sufficient for Q, that means if I know P is already true, it is a sufficient reason for Q to be true as well. That's also talking about causal relationship. So it really boils down to a similar interpretation. Yes, Chidalu.
Is it like saying if P is true, then like the truth value of the whole expression depends entirely on Q?
Exactly. Very good. That's another way to see that. Let me repeat what you just said. If the cause over here is already true, then you're right. Whether or not the causal relationship is maintained depends on the consequence. Because somehow, when we talk about causal relationship, we're saying that the obligation over here should only matter if the cause is already true. Otherwise, it doesn't really matter what this is, given that the cause is already false. There's no obligation for consequence to be true. Yes, that's another way to see that. Alrighty, so we are done too. The next one is only if. This might be the trickier one, but that one's not too bad. So when I say P implies Q, and then I say it's equivalent to saying P only if Q. Okay? One way to think of it is like this. I'm going to switch to the truth table in a moment. If I know that P is already true, then the only way for the entire implication to be true is when Q is also true. All right? Ooh. Good? That's okay. Don't worry. Okay. Now, guys, are you okay with this? It's similar. You know, I'm basically saying around the same thing, but just a slightly different interpretation. Let's see this. Okay, when we say P only if Q over here, let's write down over here. P only if Q, right? This one is to say, if I know that P is already true, okay? So you can see these are the two cases. Okay, if I know that known P is already true, then the only way for P implies Q to be also true is when Q is also true. Right? Otherwise, if Q is actually not true, then the entire thing will be false. It's similar. Guys, please. Yeah, everybody can hear you. Yeah. Okay. Do you guys actually remember back in 1021, for those of you who took with me? No, it's okay. No, it's okay to sometimes discuss. I'm just brought to my mind. I remember, yeah, I'm pretty sure not you guys, but back in 1021, the winter, it was fun, right? I even threatened the class. I might call the security. Do you guys remember that? Yeah. Don't worry, I didn't plan to do that. You know, it was more like a bluffing. You know, yeah. I'm glad people just keep quiet. Otherwise, I have to say, oh, I really gotta get a phone to call security. Yeah. Well, I'm just joking. You're fine. Yes, question. 1021. You know. Of course, you did. The first one was MATLAB, and then the Java. Yeah. All right. Anyway, you guys are good. Guys, it's definitely okay to discuss, but keep it low, please. Otherwise, the room is very quiet, so everybody can hear you. All right. For this one here, let me write it down. So if you know that P is already true, the only way for this to be true, the only way the implication is true is if, okay, only if Q is also true, right? So you can see I'm trying to use the word only here and also if here, right? Otherwise, it's false, right? And what if the P over here is known to be not true? Then we don't care. Then it doesn't matter, right? Similar reasoning. Okay? And then I will tell you what you should know for the test. All right? And for the false over here, then in this case, don't care. What Q is. Okay? The overall outcome will just be true for implication. All right, let's see the final one. And then I will give you a little bit of hints about how you're supposed to study for this. Oh, actually, two more. You will see also on the slide, Q is necessary for P. It can be interpreted the same way. This is to say, Q over here is really necessary for the implication to be true if we know that P is already true. I'll write it down first, and I'll try to be a little bit better in pointing out to the row. Okay, I'll write it down here. Q is necessarily, oh, how about this? It's necessary to be true. In order for the implication to be true. If we know exactly P is true. Right? You can see I'm trying to use the word necessary. All right, let's now try to look at the truth table again. So Q would be necessary to be true over here for this implication to be true if we know that P is already true. Right? However, if Q is necessary to be true but it's actually false, given that P is also true, in that case, of course, the entire implication should be false. Otherwise, here, don't care. Right? A very important insight into the truth table is if the antecedent is simply false, we simply don't care what the consequence is. That's a very important insight. Later on, when we do proof, either for LTL, some temporal logic property, or when we do program verification in the last phase of the course, you might just need these kind of cases just to prove things trivially. Okay? The final one. All right. And then after the final one, I'll give you guys some tips about how you may study this slide for your assessment. Just give you your own. Again, I keep saying the last one, but I do have another one. Okay? How do you prove if and only if? Okay? So here, let's say this. If you want to prove, let's say P. Oh, thank you. Guys, don't be shy. If I really forgot, shout on me. Okay? P if and only if Q. Okay? So now how do we prove that? There are two things we have to prove. One way you can kind of remember yourself is like this. When you write this, P if and only if. You can think about this part over here is the if part. That's how I remember it. This is the if part. Okay? And this one over here is the only if part. Let's write this down and then we'll see. Whenever you're writing this, you'll say P if and only if Q. If you remember that, hopefully that will always get you the right pattern. Okay, so that means if I want to prove it, prove this equivalence, I want to need to prove. Number one, P if Q. This will be P if Q. And of course, if you're not kind of bothered by this, this of course means Q implies P. The same, right? Okay. And number two, over here, you also need to prove the P implies Q. This will be the P only if Q part. Right? I'll leave you a little bit of time, maybe after class, to really think it through about how to see the position of the implication over here. But I suggest, try to remember whenever you write it, P if and only if Q. That's how you remember. Okay? Good. For your information. The final one is the unless. Okay? Q unless not P. This one here, I would suggest you really need to, if you really forgot what this really means, just remember you have to look at the truth table very carefully in the following way. Okay? And let me give you some hints just on the slides. You want to think about when is P implies Q true, and you want to look at the truth table. Okay, let's look at that. Bye-bye. I guess he might be tired. Yeah. Okay, over here, Q unless not P, right? You can think about these two are the conditions for the implication to be true. Let's look at them one by one. Okay? Think about this is condition number one. Okay, let me use a different color. How about blue? This is condition number one. This is condition number one, which is Q to be true. If I know that Q is actually already true, is it the case that P implies Q is always true? Indeed. In this case, it doesn't really matter what P is. All right, that's what really Q is saying. On the other hand, let me finish this, just in case you got a question, I can also answer. This is to say, if not P is true, that means P is false. This will be condition number two. That means P is equivalent to false, right? In that case, how do we highlight it? So now, when P is false, you can see here and also here, the corresponding value for P implies Q, despite what the value is for Q, is also true. So this unless form interpretation here is really talking about 1, 2, and 3. These three rows. These are the three rows where the outcome for P implies Q are simply true. The one that's missing is the only way to make it false. Patrick? Not P or Q? Yeah, definitely. You can think of that too. Yeah, indeed. Logically, yes, absolutely. So guys, don't forget, there's something I think on the slide too. I'll just write it here. P implies Q by definition is not P or Q. Exactly. That's another way to say that. Of course, people sometimes might prefer this way is unless, right? You know. Yes.
In this course, do you have a preference how we're going to write it?
I have no, yeah.
Arrow versus triple equals versus IFF versus...
Oh, you mean equivalence, right? Yeah. I would say we don't really make a huge distinction about this. I would say usually if I just want to say some property, I would say these two are equivalents. If there's something we may just want to perform a proof, like an if and only if, I might just write this. Yeah.
They're the same though, right?
They're the same. Well, sometimes even if I say I want you to prove this one, you can just prove the if and only if. Yeah, good question. All right, guys, how do you study this slide over here, right? I'll try to maybe give you guys some example question, maybe when it gets closer to the test, okay? Unavoidably, you have to memorize about these words, right? If and only if and etc., right? So what I would tend to do is I might just give you some logic. Oh, okay. One very simple exercise you can do, for example, is like this. I might say something like, which of the following expressions are equivalent or the same, equivalent to P implies Q, right? For example, here I might just say Q if P. I might give you, let's say I only give you two choices, and then I say Q only if P, right? But if you look back over here, you can see it should be P only if Q, right? I swapped the order. So that means this one should be considered as a good choice. This one should be considered as a bad choice. That means you should really know about where things should go very well, okay? Yeah, you can kind of make more questions for yourself. I'll try to give you a more concrete one later, but you kind of get an idea. Right. I just want to make sure you understand how to put things properly for the expression. Alrighty, good. Let's now move on. That's about implication. And do you guys remember inverse, converse, and contrapositive? Right? Oh, Shidalu, yes, go ahead before I talk about these three.
I had a question, about memorization. How can we derive that Q only if P is not equivalent to?
So it's a good question here. I think unavoidably there's got to be some memorization, but you can memorize with some tips over here. How about this? I would suggest to remember the way you write the if and only if sign, right? What I wrote before, I think that would be a very good way to remember, right? This one here. Remember the way I wrote it? I will show you again. I would say P if and only if Q. That one actually already shows to you about the two, right? So that means this part over here is the if part. And this part over here is the only if part. That one already tells you, how you can understand only if versus if, right? So I would say from there, so maybe it will be easy for you to see. Mm-hmm. Yeah. Question, guys? You okay? I agree with you. You know how I learned about this? I learned about this from Jeff. Yeah, because when Jeff, I was taking a 31-1 with him when I was a student, and that's the way he wrote it. I thought, oh, maybe that's how he remembered that. Jeff Edmonds, yeah. Yeah, did you guys take a course with him before? 31-1, fairy godmother, right? Do you guys remember? Yeah. Yeah. The bird, yes. I forgot the analogy, but I enjoy his course. I enjoy it. Did he play a magic trick to you guys in the class? Poker.
Oh, yeah.
the way to really illustrate a looping variance in the class. Yeah. Okay, maybe not. Not relevant. Go ahead. George Telakis. I didn't get a privilege to take a course with him. He's a good colleague. I think when I was a student here, I don't think he was not a regular instructor for 1090. Not really. He was more like he was a chair of the program, so he didn't teach any course. He's been here for a long time. Yeah, he's been here for a long time. Yeah, he taught me 2001 theory computation and also 3101. 2001. Yeah. Anyway, it was a fun course. All right, guys, and I will give you guys more practice question maybe when we get to the written test. All right. But this one here, I'm afraid to say there's got to be some memorization involved. Okay, the next one here will be inverse, converse, and contrapositive, right? And I'm afraid for this one here, also you need to know the form. I'll write it down together with you just for one time to see. Okay. If you got P implies Q, why don't we do an exercise at the same time? How about that? That might help you too. Okay. Let's say in this case, for example, pick it up on the fly. Let's say X, let's say it's an interval. Let's say X larger than 0 and X less than or equal to 23. Okay. Let's say we have that implies, let's say Y, let's say larger than or equal to 23, or Y strictly less than 46. Don't worry about if there's any causal relationship, right? I'm just writing them down. Let's just manipulate the symbol. That's my main point. Okay. So apparently this is P, this is Q. All right. Let's now do each one of them one by one. So when we define the inverse, yes, the first one, inverse. By definition, it's going to be just put negation on both. You don't switch the antecedent and consequence. You'll be not P implies not Q. All right. How do we apply this to the example? And let's say we have I'll get to you. Let's say we have the following requirements. You must simplify any relational expression as much as possible. For example, you cannot really have, for example, not X less than 0. Instead, you are required to simplify that into X larger than or equal to 0. Let's say there should be no negation. That's a requirement. I will do it together. Thomas, you got a question? I answer that? Okay, awesome. So to really, let's do that. Okay, we definitely need De Morgan a bit. All right. Not P implies not Q. Let's now try that. So that means we got, let me just start with that. So not X larger than 0 and X less than or equal to 23 implies not Q. Not the case. You know what? Let me make some room over here. Y larger than or equal to 23 or Y less than 46. And we need to simplify that. And that one will be just equivalent to, and we can do De Morgan. And De Morgan is actually mentioned just in the next slide, but let me remind you right away. Okay? If you got not the case, P and Q, it will be not P or not Q. If you got a case not P or Q, will be not P and not Q. Think about you're distributing the not over n. What you will do is switch from n to or, and then put negation on both, and symmetrically for the other one. Okay, quick review. And the way I'm writing this kind of style over here, I want to also mention that briefly. That's something you'll be required to write certain proofs when we get to the program verification. It's called equivalence proof. I'll write it down here. More to come later. Okay, it's called equivalence proof. Equivalence proof in equational style. Yeah, not too sure if George actually taught you the same way, maybe for equational stuff. Maybe not, right? It's there. Yeah. You always prefer?
No, we prefer this.
Oh, you prefer this. Okay.
Over is like
Okay. Okay. Good. Okay. Good. Okay. Let's now do this. Okay. So now let's try to De Morgan twice, right? This will be x less than or equal to 0 or x larger than 23. Are you guys okay with this? Anyone, if you think you're not really following this step, please don't be shy. Raise your hand right away. It's important for you to understand. I might give you something very similar in the written test. Okay, good. Implies, and De Morgan twice, y strictly less than 23 and y larger than or equal to 46. That will be the answer. That's the inverse. Okay? Inverse is good, and converse is actually very, very easy. You just switch the antecedents and consequence, for which I'm going to put it here. Let's say purple. Okay, converse. Sorry, let me just make sure I got the name right. We just did inverse and converse, absolutely. Okay, so for converse, over here, if you look at the definition, there will be no negation involved. You just switch the two, all right? Converse, what you will do is you will just switch this one here and this one here. So it's going to be y larger than or equal to 23, or y less than 46 implies that used to be the antecedents, x larger than 0 and x less than or equal to 23. Converse. Okay? The final one, right? Sorry, being a little bit disorganized over here, but I want to put all the three in one page. The final one. The final one, I'll put it here. Okay, contrapositive. Contrapositive. Basically, you can think about it's going to be the converse of the inverse. All right? Converse of the inverse. Or inverse of the converse, doesn't matter, the same. Okay? Now, how do we do that? Let's say we already got the inverse. This is what we got. This is already the inverse. We take this one here and switch. And this consequence to antecedents, antecedent to consequence. That's all we got to do. Okay? So it's going to be y less than 23 and y larger than or equal to 46 implies this one here used to be the antecedents, x less than or equal to 0 or x larger than 23. All right? Are we okay with these three? And I'm sure you guys know, you used to know. These three forms over here, one of them, either this one here, the inverse, or this one here, the converse, or this one here, the contrapositive, one of them is logically equivalent to the original implication. Which one? Contrapositive, exactly. You actually got one theorem just called contrapositive, right? Very good. Yes. I'm not too sure if we get there, but anyway, if we get there, I'll let you know. Absolutely. All right, so axiom over here, right? So for this one here, let me just review together with you quickly, okay? And then we can take a very short break before we get to predicate, okay? So we're gonna go over, I want to go over just about, definition of implication. P implies Q by definition, not P or Q. That one's easy, right? And identity is an interesting one. I want to talk about identity and also zero, these two, okay? I only listed the one for implication. But interestingly, for other logical operator, you also got identity, also got zero. Let's review them very quickly, okay? So let's talk about identity first. Identity. The first one was if I got true implies P, I will just get P. What does that mean? That means if the antecedent is already true, the entire thing depends just on P. Pretty much like a remark that Chidalu made before. Yes. Patrick.
Oh wait, actually, can it also be read? Like, what's the order of precedence here? Is it the equivalence or is it the
Oh,
implication?
okay. Precedence, yes. Equivalence is definitely the lowest one, always. So that means in this case, even if we didn't bracket that, it's as if we put a bracket over here. The antecedent is going to be something like this. Oh, sorry, the precedence. Precedence of operators. Conjunction is the highest one. And then disjunction, and then implication, and then equivalence. That's something we can assume. Yes. I will try to look up, make sure that's also the case for TLA plus. But whenever you have in doubt, always put parentheses to force the order. Okay? Otherwise, we assume this precedence over here. Negation, yes, very good. Negation is actually the highest one. Very good. Absolutely. Negation, yes. So when we put this, it's as if you put a parenthesis over here. All right, what about identity for conjunction? Which means I want to have some form like this. Conjunction here, if I have P over here, how do I get to the original P? What should be here? True or false? True, right? Good. Awesome. That was good. What about the identity for disjunction? Should be symmetric, right? False. All right. And quick aside, what's the identity for addition? Addition, like a plus. 0. Yeah, how about multiplication? 1, right? Just for your information, right? Yeah, I'll put it here. So for addition, you see 0 plus any A would be just A. For multiplication, 1 multiplied by A is also A, right? So these are also the identity of the numerical operation. Just that one just for your information. And identity, we also want to talk about 0 property. Okay, I'll put 0 property over here. In the case of that identity, we want to find out these guys, which will make the original predicate on the right-hand side just become itself, basically, as a result. Right? But now, we want to say the right-hand side is going to be some fixed Boolean constant. That's called a 0 property. The one that's listed in your slides is the 0 property for implication. I'll write it down here. So that's false. It implies P is always, no matter what, P is just true. That's the 0. Which means the right-hand side over here, the consequence over here has no effects. Question?
That's not a question, but I'm saying if we put a bracket around the left side,
Yeah.
that also holds true. Like, for example, the first one's true implies P is equivalent to just P, right?
Oh, I see what you mean. Yeah, but yeah, you're right. If you really want to bracket this way, yes, it will still be true implies true, but it's a different one. But what I'm saying is, since here we didn't put any parentheses, it would be as if we put the parenthesis over here. Yeah. Mm-hmm.
I'm just saying, because I remember this from like 1090. It was like,
Yeah,
you have to get away from
exactly. Yep, you're right. So if you put the parenthesis over here, then you will still get the result true, of course. Okay. And guys, just to be very, very sure to remind you later, this will be as if. I have true implies P is equivalent to P. All right. And quickly, what's the 0 of conjunction? And there should be some fixed constant over here. Should it be true or false? If we put true over here for conjunction, you don't really get a fixed constant. It still depends on the P, so it cannot be true. So it got to be false. All right? Okay, so it's actually false. False because you always get false over here. And that's kind of the theoretical basis for short circuit that we talked about last time. Patrick, question? Yeah, that's fine. I think especially once we get to the program verification section, I'll do many proofs together with you in class, also assign some exercise to you. There might always be some new axioms which you can recall from 1090 you can use, but you can always say, I know this axiom.
As long as we justify the reason for doing something.
Yes, then you'll be fine. If there's an axiom, in that case you can definitely use, but it's something like a lemma.
This isn't an axiom in our system, right? This is just something we've.
Yeah, some property, yeah. I would say these ones, if that's already listed on the slides or what I talk about, you can just use them.
What about like P if
That one there, you can put in the justification there. If that's trivial, then you don't need. We can get a little bit more precise later about. I do see your concern. Yes. Of course, if a more typical scenario would be, if you want to prove something big, let's say in the exam, you might find that you want to prove a small lemma in the middle. That lemma, of course, cannot be trivial. You have to prove it separately. That might be the more often scenario. All right, guys, one more, please. What about the zero of disjunction? Should it be true or false? Yeah, so, and after applying this one here will also always be a constant. True or false? True, right? Because if you simply put true over here, it doesn't matter what P is. It would just be true. And you can see that nicely. For example, zero identity of disjunction is false. Zero of disjunction is true, right? Over here. I'm just trying to draw some connections so it's easier for you to recall. Do you really need to memorize it? I didn't really memorize precisely, but sometimes I can easily derive myself, right? I'll leave that to you, whichever way that makes easier for you. Okay? Alrighty. That's it. De Morgan, double negation, easy, right? That one you can definitely use it without proving it. Also contrapositive, you can also use it. Not a problem. All right. Any question about propositional logic? That's it. That's all we need to know to review. If there's any other axiom or property I think we should use in the class, I'll introduce it along the way. Okay? Why don't we take attendance and take a short break, and we move on to predicate logic. All right, I already got the preparation work done, so you guys can just get ready, please, on your mobile phone. Start the class, and get the question ready. Yeah, I should really get rid of F, I know. All right, check in, please. If you got any trouble, please raise your hand right away. We'll come to the podium. Guys, any question, come to the podium. Otherwise, it's about 7:18. Let's take about 3 to 4 minutes break. But don't go too far. All right, come back.
you ever decide which way the associativity and precedence is?
I'm gonna find it. I'm gonna find it out for you. But
I'm still curious.
but semantically they are the same. They're equivalent. They are. Yep. Let me show to you. I did try to look into it a bit.
So you're saying that if you evaluate like
Yeah.
pairwise, like we have like
Yeah, I'll show this to you. Yeah. Oh,
you're saying this? I don't think this is the case, right?
no, come. So what I tried was.
Is it about the attendance?
Oh. Oh, okay. Yeah, that's okay. So next time try to do a little bit quicker, right? If you do you have a pen?
I can get it.
Yeah, get a pen, and then also for you. Okay. Yes. Yeah.
This is
So.
kind of what I'm asking.
Yes, exactly.
But it's not true, right? It
I mean, it doesn't matter which way you associate, it's associative. Doesn't matter which way bracket, it will be equivalent. So I can send this to you. You know, if you try to do the truth table for PQR, it will be
Oh yeah, because the
it
only
will be
way
the
for
same.
this to be false is if R is false.
R is false, and also this, yeah, also
And
this part is
to be
true.
But for this to be true, Q
Did it work for you, or it appeared too late?
I was too late. I
Okay,
should have been faster.
be earlier. Okay, okay. Otherwise, next time I wouldn't let you sign. Okay.
yeah, it makes sense, I guess.
Makes sense, right? Yeah. The only
But this is like implying that the implication itself is like the one that you can chain. Because I know in some books they're like implication on its own. You shouldn't chain them in this way.
I'm pretty sure you can change because I think there's a one rule called shunting,
Yeah.
right? The shunting rule.
Yeah.
I think something like this. If you got P implies, yeah, something like this. Q implies R. It's a different one, right? It's equivalent to, I can combine P and Q implies R, right?
Yeah.
I'm pretty sure you can chain them, but we don't use that quite a lot.
Or this is like implication theorem.
Yes, that's something, of course.
This is like the meta theorem but applied. Okay. Okay.
Yeah.
Makes sense. Okay.
Good man. Yes. Oh, got trouble?
No, that's fine. What's the point of the identity and zero? What are those
Oh,
called?
you mean what? Okay, okay. I like a question here. Okay, let me just make sure I really understood. Are you asking what's the use of introducing these?
These,
Well,
exactly, yeah.
okay, I think you can think about these are more like a very basic patterns for conjunction, disjunction, implication, just demonstrating the property of this operator. So that's why
Properties, okay. I
property.
like that word, yeah.
Yeah, exactly, like a property. So property in the sense that later on, if you do proofs, and then when you boil it down to the base cases, you may just need to use them. Or sometimes, let's say for example, let's say sometimes you might just be able to show that you want to prove certain implication, and P might be arbitrarily complicated, but you know that you can already simplify the antecedent to be true. Then you can easily conclude, oh, it's gonna be P, right? Something like that.
Okay. Makes sense.
That's the point. Okay, good. Guys, please, 1 more minute. All right, we should resume in just 1 moment. Get ready. All right, let's get started again, please. Okay. Yeah, we got about roughly less than 30 minutes, and I will try to do as much as I can, but I do have slightly harder exercises. I can leave them clean for you guys to consider over the weekend, and I'll tell you the answer when we come on Tuesday. If we have time, we can go over them too, okay? So what should we talk about for predicate logic? Basically, there are 2 extensions to propositional logic before the break. Universal quantification and existential quantification. You definitely need both. And we need these 2 operators to define certain operators in LTL, linear temporal logic. So let's now make sure we review properly. All right, predicate logic. I'll show you the syntax very soon. Okay? A predicate is a universal or existential statements about objects in some universe of disclosure. Here, universe of disclosure, think about it's more like a collection, more like a range. Okay, let's see the syntax right away. All right. Here, this is more like, since at least when you took 3342 before, I'm pretty sure either with me or not, you study about a little bit about Rodin. This is how they specify quantification in Rodin. I'll show you how you can do it in TLA+. Both are really equivalent. But the TLA one is a little bit implicit about certain things. I'll show to you in a moment. Okay? Let's understand this part over here first. And I'm pretty sure you guys know this is universal, right? Universal. This one here is existential. Let's start with the very basic. And then the R over here is the range. Okay? That's really the range. And indeed, that's the universe of this closure that's really referred to in the slides that we just read of this closure. And whenever you say it's a range, or maybe it could be potentially a set or collection of values, you always want to think to yourself, what if the collection is empty? What should we do? Right? So in the case of universal quantification, if this range can be shown to be empty or just false, what's going to happen? And also in the case of existential quantification, if the range can be shown to be false or empty, in that case, what should be the result? Right? We'll get there. And there is an implication over here by the definition for universal. This is to say, for all the I, such that if I happen to be in the range, then we must make sure P is satisfied. What if I is not in the range? We don't care. Okay, let me write it down. So that's why we got implication over here. So this is to say, I in the range. Then P I should be true, must be true. Otherwise, the whole universal quantification will be falsified. Must be true. Case number 1. Case number 2. I not in the range. Then don't care. Okay, we'll see some example later. And over here, this one here, the way to interpret that is, we want to say there is at least one element in the range, and that particular element satisfies this property here, right? So it got to be both. If we cannot really find such an element that's in the range and also in the property, we know that the existential property failed. Okay? Are we okay so far? Jora? Yes, exactly. Absolutely. I'll write it down. It's good connection. The one over here, when we say don't care, and you want to look at the zero of implication, because false implies anything will just be true. Absolutely. All right? And this actually will be very beneficial later on when we talk about proof strategy. We'll get there. Okay? Let's now go a little bit further. Okay? And I want to draw a little bit connection to base cases in programming. A little bit. I'm pretty sure you guys know how to program recursion very well, but I want to draw some connection. Okay? Back in your maybe 1021 or maybe the programming course, let's say I have 2 Java methods. I'll write it down and then we'll discuss. Let me put it here. Let's say one Java method is going to return a Boolean, is an accessor. And let's call it all positive. So integer array A. Okay, and then we're going to put some implementation code over here. Let's say you want to define that this method here recursively, let's say. Of course, you got to define the base cases and also recursive case, right? Let's only worry about base cases. That's what I want to focus more. Let me give you another method here to make comparison. Let's say Boolean over here, sum positive. And then integer array A, also a collection. You can think about the A here is like the universe of this closure that we're talking about, right? Like a collection, like an input that we want to consider. All right, let me do a little bit more coding, and then I will ask you to fill out the blanks and then justify. Inside over here, the base case would be, let's say, if a dot length is equal to 0, and then I'm going to be able to just return some value over here. Don't tell me just yet. Think about it. And we have something similar. if A dot length is equal to 0, empty array, empty universe of disclosure. And then we're going to return another value. All right? Of course, it can be either true or false, right? Again, you may want to take a guess, or you can base your answer on the universal versus existential quantification. Oh, you think?
I say they're not different at all.
You mean they'll return the same value?
Yeah, for the same reason.
Okay.
Because if the array is empty, both conditions are vacuously true. It is true that everything in the array is positive. It is true that something in the array is positive. That there exists something in the array is positive because there's nothing in the array.
Okay, interesting. I kind of agree with the first one, but not the second one. Anyway, Jora, go ahead. Aha. Yeah, okay, that's good. What Jora said, I mean, collect maybe different thoughts, and then we'll talk about them all together. What Jora said was about this one here. The existential here is about conjunction. Should be an element that's both in the range and also should be satisfying the property. But the problem is, for empty array, there is no such element that will satisfy the range constraint. That's why it's empty. Because in that way, we're going to falsify this conjunction, so existential here should be false. Okay, very good. I'm going to repeat once more when I hear everybody's thought. Yeah, go ahead. How about, you want to talk about first one or second one? Which one do you want to talk about?
Are we asking if both of them are equivalent? Is that the question?
Oh, no. Okay, so what we are trying to do here is, okay, so this one here should be some answer, this one should be some answer, and this one here should be based on this one here. And this one here should be based on over here. That's the overall picture.
Okay.
So do you think the first one here should be true or false?
I think the second one thinks about it.
That's okay. That's okay.
The question was if there's equivalent, I would say they're not.
Of course, they are not equivalent, right? Guys, let me mention one more thing. Okay, this one, indeed, we want to make sure we discuss properly. Whenever, of course, the name itself may not just tell you all or some. So you want to judge to see whether the method itself is trying to ask you, do I want to make sure every element in the input array satisfies a certain property? If that's of that kind of nature, it's called universal property checking. Universal. And for those of you who took 1021 with me, if you still have the slides on your computer, I would suggest verify for me. I'm pretty sure I mentioned that maybe once, maybe somehow once. And I told you guys, maybe at this point you wouldn't appreciate it, but later on, when you get to the later year, you will see more. Now would be the time. I might be wrong, but I'm pretty sure, almost certain I mentioned that, but that's okay. Yes, go ahead.
I think answer. So the first one, I think it's you return true.
Because?
Because based on the domain, if the domain is empty, then all
Yes.
all of an empty domain.
Yeah, exactly. Yeah, domain.
And then the second one, I think it's false.
Mm-hmm.
And I think on the basis of, again, if you have an empty domain, you can't find the value.
Yep. Yeah, basically, yeah. You can think about in the case where the input array, or you say the domain is actually empty, basically the range over here would just be false. So having a false left-hand side for implication and having a false for the conjunction has different consequence, right? Right? Okay, let me write it down just to make sure. Guys, let me just say this one will be existential property. Make sure I write down everything you should know, but you gotta think about it. This one here, I would say, is more important to understand what we are doing here. What should be the answer? Let's write down the answer first. This one here should be true. This one over here should be false. One way to think a little bit more intuitively, let's say without looking at the predicate just yet, I mean looking at these two predicates just yet, you can think about the reason that this should be true is because no counterexample or another way to put it, witness of violation can be found. It's something weird. It's like I walk into an empty classroom without any one of you. I said, everybody here in the classroom got A+ in 4315. That's true. Symmetrically, I can also say everyone in this empty classroom actually got F. That's also true. So empty collection over here is a very special range, such that you can argue any property on that. It's just a property. All right? That's the intuition about why this should be true, because in the empty array, you just cannot find any number that's not positive. So that's why the property is true. Okay? And how do we understand the second one intuitively? This one is a little bit easier. Because the array is empty, so we cannot really find any positive number. To really prove that our existential property is true is easier. You just want to find one witness, but you cannot find it, right? Because no witness of satisfaction, satisfying the property. Sorry, this one, I'm just going to write a little bit more. Satisfaction. Can be found. All right? That's the intuitive way to think about Sana.
How come for the first one you assume that they are all true or all false, but you can't assume that there could be one positive and the second one?
Okay, sure. So the very important context is over here. Remember, we're talking about this line over here in the context where the array is actually empty. The array being empty, that means there's no element there. You cannot find any element there to prove that the property is false. So that's why we can conclude the property must be true, since you cannot contradict it. That's really the intuitive thinking. And if you look at the logic over here, in order to really get implication to be true, a trivial case is if the range predicate here is just false. False implies anything. That's the zero of implication. Okay? So you want to really think about this guy over here. Think about empty array means R of I is simply just false. This would mean false implies anything will just be true. So the true here really corresponds to the true over here. All right? Yes?
How come when we're defining these quantifiers, we're not just saying for all I p of I, there exists I p of I, such that p of I...
Oh yeah, that's very good question here. That's actually the way that, I see what you mean. Yes. Yes, very good. The question was, let me try to answer. How about this? Let me just finish this part over here for symmetry, and then I'll address your question. Okay, good. So guys, I'll definitely talk about your question in a moment. But let me just finish this one here. So when we talk about existential, if you think about this part over here, okay, right here, empty array means Ri is actually false. However, since now for existential quantification, it's really the nature of our conjunction over here. So that's why we have false and P is equivalent to false. That's the zero of conjunction. So that's why you see the false here and the false over here. Okay? Now, back to your question. It's a very good one. Maybe back in your 1090, this will be how you write the quantification. You simply say, for every I, and then you just say property I. And also there exists I, and then you say property I. Okay? The reason is, the reason that we spoke about this particular pattern in 3342, because we know that this kind of a pattern will be translated into some formal verification tool, like a Rodin. And Rodin itself kind of knows that whenever you talk about universal quantification, there is some implicit notion about implication. when you actually have the range and also the property, there should be some implication in between. And for the existential, it should be a conjunction in between. So that's why they kind of fix that pattern for you. That's why we did it that way. Of course, in the most general form, you can do P and P here. The P here is really this guy here. And the P here is really this guy over here. But for TLA plus and for Rodin, the formal verification tool, usually they don't really support this general form. They just have some more commonly used form for you. Yeah. Okay. Yeah, like a model, right? Just like a pattern for modeling. Yeah. This one is nothing wrong, okay? But just that for tool to really compile, you kind of need to use this kind of pattern. Okay. All right, guys, maybe think it through, right? I'm pretty sure this time recording will be fine, so you can actually repeat the recording, right? Let me say a little bit more about TLA plus, right? And then I got 10 minutes left. Hopefully, I can do a little bit more. Okay. In TLA plus, let's compare. Let's compare Rodin and TLA plus, and you will see what you should really watch out for. In Rodin and also TLA plus, of course, for this course, you only need to worry about TLA plus. In Rodin, let me just repeat. You did something like, of course, do you remember the for all symbol? Yeah, very good. Okay, I'll put it here, right? So this is for all, okay? For all x, and then it is the case that, actually, let me just see here. Yep. So you got R of x, and then implies P of x. And also existential is like a hash sign, just for your information. You don't need to know this for this course, okay? I'm just mentioning that. Of x implies P, and, of course. And P of x, right? This is for all, and this is exist. And what about in TLA plus? TLA plus is a little bit trickier, but it gets a little bit closer to what you just mentioned, a little bit closer. For all versus there exist. Okay? And then you have to somehow specify the range over here. I'll give you one example. You may say x is a member of natural number. Don't worry, I'm going to talk about this maybe in some later lab. Right? For now, I just want to give you some look ahead. You want to say some dummy variable x is a member of this net. If this in some way is specifying a range predicate. And I might say another one. Sorry, let me just write a little bit better. X in natural number, comma, y in integer. And then you've got to put a colon over here, and you might say some property, right? And you can put whatever property you like over here. And similarly for existential. You can also say x in natural number, and also y in integer, and then you got a colon over here, P of x. And here, that's what I meant is implicit. This colon over here really means implication. And the colon over here obviously really means conjunction. That's implicit. Okay? So the syntax, absolutely, they're different. But what they really are referring to as the underlying logic is really the same. Okay? That's something I want to point out. But don't worry, we're going to do practice in TLA plus later. That's about the syntax and the meaning. Okay? I got about 7 minutes. I wouldn't go over time, so let me go a little bit more. And then we definitely can finish everything rather quickly next time. Okay? And just remember these two notions about integers and also natural number. That's what we write on the paper. Okay? Over here. So you got this one over here would be the natural number. And for this course, our natural number definitely includes 0, like 3342. For this course. Just remember, 0 is included. And also we got integers, right? Like a z. That'll be integers. And it will be basically minus infinity all the way to 0 and all the way to plus infinity, right? Conceptually. And also includes 0. All right. Just for your information, and let's go a little bit further, see how further we can go. Universal and also existential. Right? We talked about informal meaning already, all versus some. And what we need to now talk about will be some proof strategy. Okay? About 5 minutes. Oh, how about this? The final one, I will talk about next time. Proof strategy for universal quantification. I'll talk about how to convert between. And finally, I'll give you a little bit harder exercise. Okay? But you can feel free to try over the weekend. So what I want to do now, just do some simple exercise together with you. And we are done for today. Okay? Let's say these. 5 minutes should be enough. Okay? Every one of them should just be evaluated true or false, right? How about the first one? True? Because, well, obviously, natural number here by definition will be 0, 1, 2, all the way to plus infinity. Of course, every one of them will be larger than or equal to 0. This actually exemplifies one proof strategy for us. If you ever want to prove a universal quantification is actually true, one way to prove it is you want to say all the m members in the range satisfy this property. Another strategy, if you're lucky, if you can show that the range is empty, then you prove it trivially. That's something we'll talk about on Tuesday. But for now, I just want to mention. And all elements in the range larger than or equal to 0. So that's okay. What about the second one? False, right? And this exemplifies how you can disprove a universal quantification. You just need a witness or counterexample. Give me a witness. -1? Absolutely. So now think about what's happening here. Here, if I can find, let's say, witness, or you can say it's a counterexample. When you want to find for like a violation, you can also say this counterexample. When you use TRA plus in like a part 2, you will see there's a word called counter trace. Whenever there's a violation of the invariance, they will give you a counter trace, meaning that assistant trace that will lead you to some violation state. That's something I will address in the part 2. Counter example. And -2, for example, right? Now, if you think about it, if I substitute into it, -2, a member of integer, implies -2 larger than or equal to 0, right? I just substitute I over here by -2. If I do that, -2 is an integer for sure, true. Implies -2 larger than or equal to 0, false. True implies false, false. All right, that's how you show it. All right. Okay, third one. False. Okay. Oh, okay, so let's say witness, right? I will be, let's say, 2. And J will be maybe 2. Yeah, basically when they are equal to each other, right? And for this one, you can definitely try to substitute. 2 is a member of integer, and 2 is also a member of integer. True and true is going to give you true for the antecedents. Implies 2 less than itself is false. 2 larger than itself is also false. False or false will be false. In that case, you got true implies false. Let me write it down, just in case you got lost. We still have just 1 minute. So think about 2 integer over here, and 2 is integer, implies 2 less than 2, or 2 larger than 2. And very quickly, you can see this part over here is true. This part here is true. This part here is false. This part here is false. And then true and true is going to give you true. False or false is going to give you false. So you got true implies false is going to give you false. All right? Good. Hopefully you're following. Okay, very quick. How about this one here, existential? True. And in order to prove that existential quantification is true, you show one witness of satisfaction. What value? Well, you got to give me one value. That's the witness. 0? Yeah, sure. That works. Yes, absolutely. Oh, sorry. Oh, what did I do? Sorry, somehow I went to 3342. I'm not too sure why. Okay, a witness, guys, bear with me, almost done. Witness over here will be just 0. So 0 is a member of natural number is true. And 0 larger than or equal to 0, right? You're going to get true and true. So it's going to be true. All right, what about this one here? Also true, right? Same, okay, same witness, very good. That one I'll leave to you. What about, oh, one more thing. If you see this one here and this one here, by just switching the quantifier, it's going to go from false to true, right? Just notice that. One more, that's it. What about this one over here? True, witness. 1 and 3, okay. Let's say I will be 1 and J will be 3. Sure. And guys, try to use the same substitution like this and use 1 and 3 over here to justify it will be true. Okay, I hope it's not too fast. We can definitely finish this in the first half, and then you definitely see some temporal logic on Tuesday. All right, thank you. I'll see you next week. One moment.